Hello, my name is Jae-won Kim. I'm from Korea Institute for Advanced Study. And this session is organized by the Korean Physical Society and the Korea Institute for Advanced Study. And this is a special session on quantum technology. We invited Professor Jungsang Kim at Duke University, and we'd like to hear a welcoming address from the president of Korea Physical Society, Professor Sung-Yun Hong. Let's welcome President.
Dear KPS members, I'm Sung-Yun Hong, as introduced, the president of Korean Physical Society. It's my great pleasure and honor to welcome you to today's plenary lecture sessions. In the celebration of the 100th KPS General Meeting, the Korean Physical Society organized the Quantum Technology Special Session and Symposium. And for these special occasions, we have chosen the quantum science technology as the theme of the plenary lecture sessions. We are privileged to have invited Professor Jungsang Kim from Duke University as our distinguished speakers. Professor Kim is globally recognized for his expertise in quantum computers, a pivotal field within quantum information science technologies. While Professor Kim cannot attend in person, we are delighted to offer you the opportunity to enjoy his lecture online and offline together. In addition, all the quantum sessions will be broadcast online, allowing all KPS members to participate in the experience from any occasions. I trust you will thoroughly enjoy the quantum session and including the plenary lecture sessions. Thank you so much.
Thank you, President, Professor Sung-Yun Hong. Okay, let me briefly introduce Professor Jungsang Kim. Professor Jungsang Kim graduated the Seoul National University, and he entered the Seoul National University on 1988, so-called Olympic class. Do you know what the Olympic class is? And he got the PhD from the Stanford University with Professor Yamamoto. And actually, Professor Yamamoto's laboratory produced many good quantum information scientists. And then he moved to Bell Laboratory, and he worked on a very complicated machine, micromirror array multiplexing coupler for many years, and he succeeded in developing that one, but I heard it was not very successful at market because technology changes. And then he moved to Duke University, and I visited his laboratory for my sabbatical leave, and it was year 2007. And at that time, he was building up compatibility for capacity for the ion trap quantum computing, and he was organizing human network, expert network, and he was working on very hard the ion quantum computing ideas. Now he stepped away from the CTO of IonQ, but I guess he's preparing next step. And he worked on this project so hard, and he organized a human network. And so I think he can share his experience with our Korean physicists and young physicists, and not only Koreans, how to build up this enterprise. And this breakthrough in enterprise is very important for physics community. And let's welcome Professor Jungsang Kim.
All right, first of all, I would like to really thank the organizers of the Korean Physical Society spring meeting for inviting me to give this plenary lecture, Professor Sung-jae Lee and Professor Jae-won Kim and other KPS leadership. I really appreciate it. I have been working in quantum computing for the last 20 years. And I think there can't be more exciting time for physicists, but also kind of a broader network of engineers and computer scientists and mathematicians to really think about how the technology that is very rapidly evolving and continuously improving can really make an impact on how we do science. But not only science, but also on many of our industry and the rest of the community, society. I think this quantum computing field, quantum information science field, and now engineering and industry is a rapidly growing area with a lot of activities, not only in trapped ions, but in superconducting qubits, photonic qubits, neutral atom qubits. So I think the activity is very, very dynamic. And I think people are making incredible amounts of progress on all fronts. Of course, my personal experience and passion has been focused on trapped ion quantum computing. So today I'm going to mostly talk about the experience and technology that we have been building up in this field. But I strongly encourage you to consider this as one example of how big of an impact we can make. And how much more innovation, opportunities, and challenges that are ahead of us. But I think it can't be a more exciting time to be working in this field. I'll talk about my work on practical quantum computing with trapped ions. And I know this is a physics community, so we're going to start with more of a physics introduction. But I certainly want to finish my talk with a prospect of where things are headed, what's really ahead of us in the next 10 years. So I'll start with an introduction. I'll tell you a little bit about the state of the art in trapped ion quantum computing. I'll also talk about how we get to high performance quantum computing and how we can work with errors, especially coherent errors, and leading up to error mitigation and error correction techniques. I'll give you a very, very brief example of some of the applications in mostly in scientific areas that we've been working with quantum computers. And then just a prospect of what's ahead, say in the next 10 years or so. All right, so I'd like to start with my personal question, a search for the perfect qubit. When I started in the field, there were many, many platforms of qubits that were being considered. And even in the subfield of trapped ions, there were many, many questions about what is the right qubit atoms to use and so on. And I think the standard answer is pick your poison, meaning every physical platform has its advantages, but it also has its drawbacks and challenges that you have to work with. And I think the real question is, what do you think as the fundamental advantage, and what do you think as the challenges that you can solve with technology? So in my opinion, I started with a very fundamental question, which took me many years to come to realize. But in retrospect, this, from my point of view, is fairly fundamental physics. So what is a good criteria of defining a really good qubit? And here I say perfect, and I know scientists have always concerns about the word perfect, but can you actually think about a good criteria for defining a really good qubit to work with? So a qubit, as we all know, is a very simple two-level quantum system, two energy levels that we can access. And in an ideal world, there's only two levels that are involved and nothing else. And usually in any physical system, you really want some energy separation between these two so you can actually address them. If they're energy degenerate, then it's very difficult to manipulate those systems, although it's not impossible, it's really hard. So you think about a two-level system with some energy difference, and that energy difference is actually characterized by the characteristic frequency. And then you think about creating a quantum state with both characterized by a point on this Bloch sphere. And Bloch sphere is characterized by two angles. One is theta, which is how much weight do you have between 0 and 1, and the other the phase, which is the relative phase between the two states. And this phase is very quantum. There is no analog in classical bit about this phase. And if you borrow NMR language, any noise in this theta and phi really recognizes the degradation of the qubit. So if you actually store a 1 qubit of information in your quantum bit, you want that information to be stored for a very long time, okay? And the time scale over which this theta changes spontaneously is T1. And time scale over which this phi changes, the relative phase changes, is referred to as T2 in NMR language. So if you have a qubit that's stored, and if it does not have any decay or dephasing, meaning T1 and T2 goes to infinity, then by definition, I think you have a really good qubit to work with. One very interesting question is the hyperfine ground state of an atom. And this is where you have an atom with some nuclear spin. In an example of a hydrogen atom, which has one proton as a nucleus and then one electron, which actually has a spin. Both of these are spin 1/2 particles. And then when they interact, that electron spin to nuclear spin interaction is called a hyperfine interaction. And that hyperfine ground state of hydrogen has an energy level very well known as 1.2 gigahertz hydrogen line. And that hyperfine line actually has an estimated T1 time of about 11 million years. Okay, of course, we can't really measure them because nobody can wait 11 million years, but it's calculated to be that, which means that this is a really, really long decay timescales. Now, when you think about the ytterbium qubit that we use, it actually decays about a factor of 1,000 times faster because the energy time is about 10 times longer. But it's still going to be measured in thousands of years. So the spontaneous emission that flips this T1 for hyperfine qubit in a ground state of an atom is really very long, fundamentally. And therefore, that also allows us to really measure the energy difference between these two very, very accurately. In fact, we realized in the 70s, the physicists realized that this energy is probably the most stable two-level system we can think of. And then we actually started to use this to define time. Define time means we have now defined an atomic clock, and our 1 second is actually defined by measuring a energy splitting between hyperfine ground state of a cesium atom. And in cesium, therefore, this energy splitting between the hyperfine ground state is 9.192631770 gigahertz. And this number is actually exact. Exact means that there's no error in this. We actually use this to define 1 second today. Okay, we don't use astronomical like the sun evolving around, Earth revolving around the sun, and that kind of a reference to define a second anymore. We use atomic physics, and that's exactly the physics that we can actually use. And what this means is when you have a hyperfine qubit, it is your ability to isolate them from the environment that actually dictates how long the T2 time is. There's no fundamental intrinsic T2 time. It's really limited by your technology. And this is a great example of Professor Ki-Wan Kim at Tsinghua University about 3 years ago. They measured a coherence time of over 90 minutes. And in his words, what this means is before the start of this lecture, I can set the coherence time of my qubit. And by the time we're all done with Q&A sessions, the qubit will remain continuously coherent. Okay. All right. So what this means is this is a really, really, really nice qubit system to work with. You can store qubit in quantum information in this qubit, and it will actually stay coherent for a very long time. Okay. It's a really ideal system. But it doesn't mean that we know how to build perfect quantum computers with it. It just gives you a really promising platform to work on. And all errors using these quantum computers actually originate from our ability to isolate and control these qubits. Okay, so what this means is if you pick this qubit, now a lot of your making better quantum computer is very much a control problem and system design problem, and therefore you can actually start to, based on that fundamental physics understanding, you can actually start to really build and engineer good systems. Okay, and that's the approach that I and a lot of my collaborators have taken on trapped ion quantum computing. Okay, so with that, a very basic foundation, where do we stand? And even in trapped ions, there are many, many different atoms people are using. The most, in my mind, the most well-developed technology qubit platform is this 171 isotope of ytterbium. Actually, there are several quantum computing companies based on this. And the two major trapped ion companies in the US, IonQ and Quantinuum, have developed their systems based on this technology. So this is where we are. Initialization of qubit is done by what's a process called optical pumping, a very well-known atomic physics process. And the fundamental limit there is estimated to be about 10 to the minus 6. And we can't measure that quite yet because we're not limited by initialization. We're actually limited by state detection. And state prep and state detection, really, you can't distinguish the errors between them. So we have very, very good initialization capability. The qubit measurement is performed by resonant fluorescence. And very high fidelity state detection can be established in this process. 10 to the minus 4 is fairly routine these days. And people are really pushing the utilizing different atomic physics, physical processes to see if they can push this fidelity down below 10 to the minus 4. And so there are people making really good progress on this. And then the single qubit gates can either be driven by microwaves or by Raman transitions. And Raman uses laser beams. That's kind of the approach that we have taken. And here, the fidelity is really limited by spontaneous emission of the laser, which is in the 10 to the minus 4 to 10 to the minus 5 range. If you actually use microwaves, there is no spontaneous emission. And people have demonstrated 10 to the minus 6 single qubit gate errors. And there's really, there isn't even a fundamental limit to that. So we can really build a very, very high fidelity single qubit gates with this. The current performance limitation remains in 2 qubit gates, which is now driven by state-dependent force from Raman transitions. And in this case, in order to make 2 ion qubits interact, we actually have to use their motional coupling, meaning their Coulomb interaction. And that motional degree of freedom is less perfect than the hyperfine qubit of the atom itself. So while you have to transfer some of that quantum information into these motional degrees of freedom before you make them couple, and that actually limits, mostly practically limits your gate performance. So people have recently reached better than 10 to the minus 3 errors using these qubits. And I think people believe that they can push it even further down. So you can actually see that we have a really good component technology to build very high performance quantum computers from a physics point of view. Now, I would like to see if I can just focus a little bit on the high intensity, high fidelity entangling gates, because that is the most important process that we can utilize. The most important process for building quantum computers. As I briefly mentioned, the entangling gates utilize the quantized motional modes shared by the qubits to mediate the interaction. And the first proposal was established in 1995 by Serac and Zoller. And this is a very famous paper that actually really started ion trap quantum computing field. A few years later, Klaus Malmer and Anders Sorensen came up with an improved scheme that makes the gate performance more robust against kind of motional noise that's in the system. This so-called Malmer-Sorensen gate has been the workhorse of quantum computers for a very long time. I would like, if you look at it very briefly, the way we generally create this in our scheme is you start with a long chain of ions, and then we have a focused laser beam that can address individual atoms in this chain. And when what we would do is we would tailor these laser beams so that the atomic motion, the atom actually gets shifted from its central point, either up or down, depending on the internal state or the qubit. So if the qubit is in 0 state, the atom will get pushed up. If the qubit is in 1 state, the atom will be pushed down. And this is what we call a state-dependent force, okay, or spin-dependent force. And what this allows you to do is when the 2 ions are in the same state, both up, up, or down, down, or 0, 0, 1, 1 state, then both of them get pushed in the same direction, and therefore their relative distance does not change. But if they happen to be in the opposite states, then one of them will be pushed up and the other one will be pushed down, and you have a slight increase in the distance between these 2 qubits. And that slight increase in the distance actually introduces a small energy difference that looks very much like a dipole-dipole interaction. And that energy difference will actually lead to a phase shift depending on how long that distance change is maintained. okay? And if you hold it for just the right amount and bring it back into zero, then you can actually accumulate a finite amount of phase angle for the two states that are in the opposite direction. But obviously, you don't know whether the up, down, or down, up, both will accumulate exactly the same phase in an indistinguishable way. And that allows you to actually create this non-trivial phase accumulation, which lead to entanglement, okay? And that mechanism is basically the foundation of Momo-Sorensen gate. And we can actually do pretty high fidelity gates these days using this approach or interactions that are very similar to this. And today, most of the commercial quantum computers that you see based on trapped ions utilize this form of interaction as their foundation of their gates. Okay, so that's been very successful. People build commercial systems today, but there is actually a lot of new or even old interesting ideas that you can push forward. Now, if you look at the history of 2-qubit gate errors as a function of time, the trapped ions actually have led the way in actually improving the 2-qubit gate errors or 2-qubit gate fidelities. But superconducting qubits and neutral atom systems are actually catching up very quickly, and their performance is also improving over time. But once you have the foundational 2-qubit gates in your system, then you actually have to start building quantum computers that can do useful stuff. And all of that engineering and system creation and software building, all of that is kind of what we need to continue to build our communities to interact with engineers and interact with computer scientists with a physics foundation, so we can actually make much more substantial progress in this field. Now, there was a very interesting question of instead of you can in principle break all of your universal quantum computing down into 2-qubit gates and single-qubit gates. But if you have access to multi-qubit gates and body interactions, then certain problems can be done much more easily. So in this work, we actually have revisited the Dirac-Zoller gate. That was the very first proposal for quantum logic gates. And in this case, if you can actually improve the experimental conditions, then you can actually create a control NOT gates. And here you can have as many controls as you want. In this example, we have a control NOT gate. It's a 5-qubit gate, Toffoli 5 gates. And this type of gates can actually be directly constructed using a Dirac-Zoller interaction. So we have recently done this experiment, and we can actually create a 3-qubit Toffoli, which is a control NOT gate. We can do a 4-qubit Toffoli, which is a control NOT, and then a 5-qubit Toffoli gates, control NOT gates. And this kind of scalable logic of multi-qubit gate operations can actually be constructed. In a similar way, recent progress have realized that even in this Momo-Sorensen type interaction, where we actually move the qubit states across a phase space. And again, this accumulated area is exactly the phase that you accumulate to create your gates. But if you actually introduce a little bit of squeezing, this is like spin motion squeezing you can do just by looking at higher order sidebands. Then it turns out that you can actually create, with a little bit of squeezing, you can create a multi-qubit gate operations. And this was recognized a couple of years ago by my colleague Chris Monroe and Or Katz and Marcus Cetina. And then we don't need a lot of squeezing, and this is a fairly routine thing to do in trapped ion systems. And then you can actually create this high order multi-entangling gate. So this shows an example of a 3-qubit gate and a 4-qubit gate. And this is not the Momo-Sorensen type. This is actually an XXX or XXXX type gates. But they have recently done experimental demonstration of both 3- and 4-qubit gates with this. So this trapped ion platform actually gives you a very versatile control where you can actually implement a very large set of baseline gate operations based on the physics and the interaction of the control that you can establish. All right, so with that, I'd like to see, okay, based on some of these really interesting physics that are still very much going on, how do we actually create a quantum computer? This is more like a commercially viable or user-friendly quantum computers. And this is actually the baseline of how we do it. So we can actually first trap a chain of ions, as I indicated earlier. And in the control system, we actually take a single laser beam and split them into multiple ways and make sure that we can address individual qubits or atoms in this chain. And initialization, as I indicated, can be done by optical pumping. This means that you shine a specific color of laser beam, and all the qubits will be initialized into the ground state or zero state. And then based on your quantum circuit, you just, you can just program your laser beams. I'll repeat this video. You can program the laser beams to induce either the single or two qubit gates between pairs of qubits or the target qubits. And we can very easily perform a single qubit gate in parallel. That's actually very easy to do if you have a ton of if you have individual control of the laser beams. And we can, in principle and also in practice, perform multi-qubit gates, two qubit gates in parallel as well. Okay, and all of that means is all you have to do is to simply program the laser beams so that all this gate is performed. And when your computation is done, we shine a different color laser beams, and some atoms will fluoresce, meaning it will be bright, and other scatter photons, and the other atoms will remain dark. And by differentiating the fluorescence, you can actually tell which one is a 1 and which one is a 0 state, and that becomes your readout. And this once you go from a qubit and gates to a processor, then you have to think about architecture. What this means is we can actually go from, if you make an analogy to classical computers, we start from transistors and CMOS transistors, which is what the devices are. And then we have logic gates, right? AND gates and NAND gates and NOT gates, these baseline logic operations we can think about. But then in order to build a useful computer that I'm using to communicate with you, we actually need CPUs and GPUs and the processors. And they actually is a combination of a lot of these gates and transistors that you can program to do the computational task. Okay, and that is very much in the engineering domain in the classical computers. But this architecture of how we assemble the circuit together will tell you what tasks your processor, your computer can do easily, and what tasks is hard to do for your computers to some degree. Okay, and today we have this FPGAs. These are field programmable gate arrays, which is basically a blank sheet of transistor arrays that you can actually program, like with a software, to program it to do certain functions. So we actually have a reconfigurable, very flexible digital circuits that are available today, which is very widely used in many classical systems that we build. But our role in quantum computer is also very similar. Depending on just like collection of transistors is not a processor, collection of qubits is not a quantum computer. You have to be able to control them and program them to do the tasks that you designated to do. And in this case, how the qubits are connected is actually really plays a very crucial role in implementing algorithms more efficiently. So it is not just number of qubits or gate fidelities or how fast the qubit, the processor, the gates are done, but also more collectively, how is the qubits assembled? How do you program it? How do you allow interactions between different pairs of qubits? All of these things factor into performing a more higher level and more complex quantum computing tasks. In a trapped ion quantum computer, and this was actually established 7 or 8 years ago now, like when you program your computers today, we use very high level programming language, right? Like JavaScript or C programming language or Raster, some of these very high level programming languages. And then the computer program will actually take the tasks that you program in a human usable language. And then they would actually translate that into machine language. They'll compile it, and they'll eventually translate it to machine language that can be run on the metal, which is the transistor array. Even some of these programming tasks today are being taken over by AI, right? So there will come a time when you specify the function that you want to implement without actually having to type in the code, and your software and AI machines will actually create the program for you. So we actually have been going through many generations of abstraction, where in the very early days, yes, we were programming classical computers with punch cards and more like machine language. But today we do this in a very abstract way. Very similar to that, quantum computers needs to be programmed based on quantum circuits that we think about. That's easier for us to think about. And even this is actually pretty low level today, but I'm sure over time this will get abstracted more. But then these circuits that we think about logically will have to be translated or compiled into the native gates that your hardware can do. Okay, these are what we call the native gates, meaning this, say, quantum Fourier transform circuit will now be translated into this control theta gates, which is easy to think about. But this control theta has to be translated into this Momo-Sorensen gates and single qubit gates your hardware can actually implement. And in our system, each of these gates now has to be translated into this laser pulses between the pairs of ions that you want. So there has to be additional kind of translation to the machine language, and eventually your hardware can actually run them. So I think if you think about this whole work sequence of a user thinking about, say, a machine learning task they want to use quantum computers to solve, or chemistry simulation problems they want to use quantum computers to solve, that logical process eventually has to get translated into execution in your physical hardware. So there's layers and layers of software abstraction and control systems that you have to build. And all of these are actually research opportunities. You think about the early stage computers. If you think about the PC world in the 80s, there was the Macintosh, and then there was the IBM PC that were competing. And then the operating system has to be built. Apple decided to build their own iOS. IBM decided to work with Microsoft to use the DOS and eventually the Windows operating system. But these types of control software cannot be designed or built without understanding what is in the hardware. But once you have a proper operating system, then the users really don't have to worry about what's on the underlying. So all of these architecture and system innovation is an opportunity to think about the next Microsoft or the next Apple. Lots of opportunity to actually make a big impact. So I think all of those are kind of, it's actually a lot of these activities are happening today outside the physics world in the industry, extremely important. And I think there is a lot of opportunity for the physics community to continue to work with the engineering community to push these types of technology progress forward. This one actually shows some of our latest data from IonQ, and this was actually published last summer. In this example, we demonstrate a 32-qubit quantum processor where you can actually do a single qubit gates, and this is actually the gate error shown in PPTT. PPTT means parts per 10,000, or 0.01% is your unit. So you can see that individual qubits on each qubit, single qubit gates on individual qubits can actually be performed in this example with about 2 parts per 10,000 kind of errors. This is 0.02% error, or 2 times 10 to the minus 4 is the average error. So very high fidelity over all 32 qubits. In our system, we can actually do pairwise 2-qubit gates across all possible pairs. So 32 choose 2. That's like 460 something pairs of gates that you will be able to do. And indeed, we can actually do all of them. You can see that the gate errors are typically in the maybe 50 kind of PPTT, 40 to 50 PPTT, meaning 0.4 to 0.5% errors. You can see that some of these pairs actually have a slightly higher errors than others, but we absolutely demonstrate that each pair, even if you get to 32 qubits, and even today they have an even larger system, that all pairwise 2-qubit gates are possible. And then what's really interesting is the fidelity and the speed of the gate operations do not depend on how far the ions are in the chain. Okay? So regardless of the distance between the ions in the chain, you can do similar performance in terms of fidelity and gate speed of 2-qubit gates. So that's an interesting architecture. There are many other architectures that people are pursuing, some based on heavy amounts of shuttling, but I think you can actually make much better individual gates based on that. But then there are other penalties you have to pay in terms of when it comes to executing circuits. So I think people are still kind of exploring all of these design spaces and then trying to figure out how to build quantum computers that can eventually run useful quantum algorithms that are hard to do classically. All right, so actually this part is one recognition. I mentioned that in our quantum computers, with trapped ions, the coherence time of the qubits is very low. And all of our errors tend to be in the control errors. And what this means is if your errors are due to control errors, you can actually mitigate those errors much better without actually having to use quantum error correcting codes. And that actually provides us an opportunity to improve the overall circuit execution, meaning quantum algorithm execution, without introducing these very, very expensive quantum error corrections. This is not only for trapped ions. I think many other platforms are pursuing and exploring this. It's just that because most of our errors are coherent errors, we can actually do this really well in classical in trapped ion systems. So here, I think this is a study that my colleague Ken Brown at Duke University have done within our collaboration in quantum error correction projects. So you can think about the unitarity of errors. So unitarity of errors means when unitarity is 0, this means that your qubit errors are due to decoherence, meaning because you've interacted with the environment has already taken information away, your quantum system has really dephased. And when that happens, then the errors are very, very difficult to fix. But on the other hand, if the unitarity is very high, your gate errors are coming from control errors, meaning sometimes you want to rotate your qubit by exactly 90 degrees, but you over-rotate it by 1% or under-rotate it by 1%. These are the type of errors that you can introduce. Now, when these coherent errors are not fixed, the errors actually accumulate faster so that your circuit actually fails with higher probability. But if you actually manage them properly and use them to cancel things out, then it turns out that your performance can actually get a lot better. Okay, so when you have coherent errors or unitary errors, then your strategy to deal with them actually makes the big difference in terms of your final success probability of your circuit. Now, I think this is, let me see if I can skip some of these. I think I'm running out of time. I'll give you a couple of examples that is relatively easy to see. So for example, I can think about a crosstalk error. So our goal is to focus a laser beam to only address ion number 1, but sometimes the intensity spills out, and then ion 0 and ion 2 also get exposed. And then when you're trying to rotate qubit number 1, qubit 0 and 1 also gets rotated a little bit. Okay. Now it turns out that there is a very well-known like control pulse techniques. That actually, so it turns out that this black line is if you start from a laser that's focused on ion 1 and you start to move the laser beam away from the ion, when the error will start to create the final result, which should be 1, and then take it down. So anything that's different from 1 is your error. And then over here, when you are 2 spots away, you really don't want when you're 2 spots away, you really don't want that ion to be addressed. Oh, sorry. But if there is a little bit of intensity spillover, then your ion will get rotated. So this black line tells you how well how robust you are against intensity noise and how robust you are against some additional spillover. But if you actually use this pulse sequence properly, then you get this red curve where the performance of your target gates becomes more flat, meaning even if your intensity is off by 1% or 2, your gate will still be perfect. And then your unwanted rotation gets suppressed, meaning even if you have a 1% intensity spillover on your qubit is not affected at all. So this kind of pulse control techniques were invented and developed in the context of NMR. This is kind of your nuclear magnetic resonance imaging that you take pictures of NMR, MRI imaging for your body in your hospital. This is very, very much of a 2-level system. The hydrogen qubit, if you will, they control hydrogen qubit to take those images. And as I said, the hydrogen in your water molecules in an atom, the coherence time of those nuclear spins are really long. So they can spin polarize hydrogen protons in your body, and then they can actually do this MRI imaging. And that technique is very similar to qubit control. So we know that these types of capabilities are there. What's really interesting and surprising is if you have a 2-qubit gate, you can think about, I'm targeting these two ions, but there's intensity spillover to neighboring ions. So there's a lot of crosstalk there. But it turns out that if you're very smart about some echoing technique, very similar to what we have discussed before, you can actually cancel out all addressing related first order crosstalk entirely. Okay. So this type of protocol, we actually discovered that, and it's a very, very simple idea. But you can actually eliminate a lot of these crosstalk errors. So if you're worried about crosstalk as an error source, don't worry about it. You can actually bring in very smart control and get rid of it, like entirely. So crosstalk in this type of systems can be eliminated without using error correction. Okay. So these are not unique. I think there are many, many opportunities in coherent quantum control where this type of progress can actually be utilized. So I have many other examples, but I'm going to skip them. So I'm going to jump to my next topic, which is what we can do with them. And here, instead of giving you concrete examples, I'm going to just highlight how much collaborative effort can be made here. So at Duke University, we have established a Duke Quantum Center. And at Duke Quantum Center, we have many faculty members who are working on various levels of the stack. So, some people work on trapped ion systems like myself, but some other people work on control systems. Some develop software, some develop, operating systems, and others work on applications and compiler tricks. So our goal is to build a vertically integrated center where we can actually start to do quantum computing research at all levels, not just the physical platform at the bottom, but also getting to useful quantum computers at all levels of the stack. So we actually currently have about 7 different versions of quantum computers that are either operational or being constructed at Duke University. And with these systems, we actually work with our collaborators, people who have ideas on quantum algorithms or some ideas they want to test at all levels. They will come to us, and we open up our system so you can actually do research at different levels. So there are people who are actually some of our collaborators at Sungkyunkwan universities in Korea, Professor Jung-gi Kim students. When all of us go to sleep here at night, they actually come online and use our quantum computers to run experiments. Right? We have a completely worldwide accessible platform to really establish collaboration so people can innovate their ideas at every possible levels. So these are some pictures of the quantum computer systems that we have established at Duke. We have about 6 or 7 of them. And many of these things are available for collaboration at various levels to actually stimulate innovation at all levels of quantum computing research. And this actually just shows you, again, you can't read all of these, but these are kind of the example of collaborative work we have done. And these are people who have ideas, but they don't necessarily have a quantum computer in the lab, but they wanted to look at, things like, gates. They were looking at, information scrambling in black holes. They were looking at Li-Yang partition function theorems, NMR spectral inference. There's all kinds of applications where people are looking to do generative modeling, which is like a machine learning exercise. So if you have an idea of how to utilize quantum computer to do something, and we can actually work with you to come up with simple demonstrations. And then if they are compelling enough, I think that gives us motivation to build the next generation quantum computers that can actually do better. Because at the end of the day, it is really the push and pull from technology and also the application needs that will eventually get us to quantum computers that can do really meaningful things. So this is nothing but a very long list of all the collaborations that we have done over the years. And the number of collaborations is on the order of, over 50 collaborations we have done. And we continue to do that. So if there are any interest where you want to try out your ideas of quantum computer, but you don't have a quantum computer in your lab, do let us know. I think we're very much open to collaboration, and DQC, the Duke Quantum Center, is exactly set up to promote that type of community building and also training along that process. Okay, in a few minutes left, I'd like to get to my final topic, what's ahead? I think quantum computing over the last 20 years came from like a physics experiment to a pretty large industry today, but this is just the beginning. I really feel that a lot of interesting opportunities and innovation is ahead of us. What are some of the things that I think is important, some key research opportunities in the next 10 years? First is, can we achieve quantum advantage in some areas? And quantum advantage here, you can actually have a more scientific definition of like a quantum supremacy, where I can do some task that is useful, that classical computers cannot do. But I want it to be a little bit more practical than that, which means that will people use quantum computers to solve their problems over classical computers? And there are a lot of scientific applications in studying materials or chemistry problems. There are people in high energy physics who are looking at quantum computing as a new framework to understand the complex problems they're facing. But can we actually get it to a level where it's so practical that people would use quantum solutions rather than classical? Okay. I think I can give you an example of internet. When the internet first came about, it was about sending data, but the bit rate was so slow that it wasn't very practical. It was much easier to put your information on the floppy disk or CD and then mail it, okay? And that will get to your destination in 2 days. It's better, you can send more information that way in 2 days than downloading stuff over the internet, right? So we started from a point where the technology was very early stage. It was actually the high energy physicists who decided to share their data from their accelerators across their collaborative network around the world. That was actually where the World Wide Web was first practically used. So I think we have examples where physics community actually have driven an early adoption of technology. And today, of course, we can't do anything without internet. Even this talk with me sitting here in the US won't be able to happen without that. So, once we actually break through on that early applications, I think the technology development will accelerate. I think more people will innovate about how to use quantum computers. I mean, I think that can actually enable new frontiers in research and problem solving. And then I think we have to work with engineers to think about building better quantum computers faster, cheaper, and at scale. Instead of building one computer or 5 computers, can we build 100,000 computers? Can we build 1 million computers? Right? In the 60s, there were probably handful of mainframe computers that were commercially available. That's kind of where we are with quantum computers. Today, we have billions of computers, and everybody is carrying one in their pockets. Right? In order to get there, we need to build better computers, cheaper and faster, and we need to invent what's equivalent to integrated circuits technology that allows us to scale the performance and cost of building quantum computers. Which again, I think today, a lot of our quantum computing approaches, we have challenges there. And then the final element is, what are the talent that we need, and how do we train the next generation of people, scientists, and also just regular general population to drive the next generation of quantum revolution? If you think about the 1980s, how many people knew how to program? You have to be a software engineer, very well trained, to be able to program a computer, right? It has to be professionals. Today, little kids can build iPhone apps and deploy it at massive scales. What this means is that over the last 40 years, we have really trained our young generation where computer programming becomes part of their standard education. Okay? And we have done this in the past too, right? 200 years ago, not too many people could read and write. Today, everybody can read and write. And based on that kind of workforce and training, we can actually build a much more advanced technology in the future. So I think we really have to think about how do we train the next generation of our next generation people to learn how to work productively with quantum computers. And I think some of these are really exciting challenges. In my mind, it's actually potentially more exciting than pushing IonQ forward, right? I think that's also very exciting. But there's just so much work that we can do to make this impact our society that I think there's a lot of really exciting work that we can all do together. So with that, I'd like to conclude. Again, I'd like to thank my collaborators over the years, both in academic and national labs and companies that we work with. Now, this is actually a picture of us at Duke Quantum Center. If you have an opportunity to visit the East Coast of the US, let us know and come visit us at Duke Quantum Center. And also my collaborators and colleagues at IonQ. Thank you very much for your attention. And
thank you. Let's thank our speaker again. And it's time for questions. If you have some question, please come forward to the microphones, raise your hand, and you come up to the microphone. Okay, I would like to ask a question first.
Sure.
Still, a lot of people are questioning about the scalability compared to others. And recently, IonQ come up with the algorithmic qubit, AQ, so-called, and comparing the performance of IonQ with other superconducting quantum computer or the optical quantum computers. And still, we have another dark horse competitor, that neutral atom by the Lukin at Harvard. And so we have a lot of surprises in the future. So could you could you tell us something about this scalability problem and comparing with others? And also people might be interested in you resigned from the CTO of IonQ, and there must be something you are preparing for some next move.
Okay, great. Thank you for that question. I'll focus on the first question. I think it's really exciting and encouraging that people are coming up with new approaches and tackling the problems in their vision to getting to scalability. But I think really, if you think about the scalability in Moore's law, we measure it with the number of transistors per unit area, right? I think that's one metric. But there are many, many other dimensions to it. For example, the cost per transistor actually has to go down exponentially, right? And then I think the cost of access to these transistors actually has to go down exponentially, and so on. But those are unidimensional metric. I think really the real scalability is how many quantum computers are actually people using, right? Classical computers. And what that means is the real scalability is in the utility, right? Initially, when first digital computers were made, it was only used for military applications, right? But today, we use computers for everything, literally everything, right? So the amount, the capability of quantum computers have gotten better. So we really have to measure the performance and scalability and usefulness from utility perspective, meaning what is the application you can run in your computer, right? That gives you better performance than classical computers. What applications can you run with a quantum computer? I don't care what type it is. Maybe ion traps, maybe superconductors, maybe neutral atoms. If any one of those technologies can get to an application that you can do, that you wouldn't be able to do classically, and people start using it, then I think we have won. Okay, so it has to be measured that way. That's the scalability challenge, right? So how do we get to the first utility? And it is not about just getting a lot of qubits. I mean, we can trap hundreds of ions, no problem, right? But if we can't control them and program them to solve a problem, like a useful algorithm, then having all those other qubits are not useful, right? It's like so the real question is how complex a quantum computing or simulation task you can run. That's the measure, and the target, meaning our real competition, is classical computers, right? In some applications, one of these approaches will have to be classical computers, right? And I think that is not too far away. I really believe that the level of control people are gaining in all of these physical platforms. Now, each platform has its own challenges and directions, but there is a lot of ways that you can actually get there, but somebody has to get there. Okay, so I really encourage people to think about the complexity of quantum tasks that you can do as a measure of scalability. Okay, so that's kind of my view, and at the end of the day, it will have to be the users that will be dictating and driving where quantum computing technology will have to go. Now, in order for the second question, I just outlined a lot of the opportunities ahead. I think if you think about, take any one of these, where is the application? How are we going to train our next generation to do quantum computing? How are we going to stimulate and create a much larger ecosystem where quantum computer is useful? And then how do we actually create the IC technology where we really invent an approach where quantum computers can be built bigger, cheaper, and faster? How do you create that ecosystem? I think there are just lots of big challenges that are still ahead, But if we can tackle them, it will have a huge impact of what quantum technology can do to our society. So I just think of that as like a tremendous amount of opportunity. And I think there are things that the company that I helped set up, INQ can do, and they will continue to do that. But there are a tremendous amount of other activities where more ideas and more innovation and more collaboration is needed. So I think that's kind of where I'll leave it. I think of there are many new things I can do. I will take some time to really figure out exactly what I want to do, because there's just too many things to choose from, but I can't do everything. So maybe I'll leave it at that.
Okay, thank you. And yeah, okay, we have one question here. Just hold on. And we in Korea, we have a lot of talents, young people, and we're Korean saying, even though you have 3 buckets of beautiful beads, if they are not threaded, they are useless. So we need to thread by networking and studying together. Come up to the microphone, please.
예, 안녕하세요. 예, 지금 강의 잘 들었습니다. 한국말로 질문하겠습니다. 예, 제가 그 양자 컴퓨터 관련해서 들었던 것 중에서 가장 인상 깊었던 것들이 이제 이 산업에서 특히 인력이 상당히 부족하다는 얘기 많이 들었습니다. 그래서 우리나라에서도 이제 대학원 관련해서 이제 양자 전문 대학원이 생기고 있는데, 뭐 머신러닝 같은 걸 보면은 이제 대학원 가지도 않고 대학 졸업하자마자 바로 이제 머신러닝 업체에 가서 이제 강력하게 이제 이 산업체가 아직 부흥하고 있는 것 같은데, 마찬가지로 양자 컴퓨터도 언젠가 아마 조만간 아마 지금 아마 교수님께서도 느낄지 모르겠지만 이제 대학 졸업자들이 이런 업계에 관련돼 진입해야 한다고 생각을 하고 있습니다. 그래서 현재 현장에서 느끼는 건 어떤지, 대학 졸업자도 가능한지, 두 번째로 대학 졸업자들이 진입을 하려면은 현재 물리 교육에서 어떠한 점들이 추가 보강이 되어야 할지, 이것 좀 궁금해서 질문드립니다.
Yeah, 알겠습니다. 답은 영어로 하겠습니다. All right, so the question is, if you look at like machine learning, there are people without PhDs and advanced degrees. People can actually get into the workforce. They can join companies and start to make contributions. And what our expectation for that is for quantum. I think there are 2 aspects of this. If you look at AI and machine learning, that field has started out in the 80s, right? I think they have about 15-year, ahead of the curve compared to quantum. And if you look at where AI was 15 years ago, in say 2010, all right, I think there were still lots of challenges. I think what really made the difference there is, the technology is more mature. You can actually go, say, if you want to, do some machine learning tasks with GPUs today, you can go open up NVIDIA tool set, and there are lots and lots of tools, software tools that are already packaged that will do certain things for you, right? You can go to CUDA platform. So a lot of those successes and powerful solutions actually now became much more widely available. And that, I think, is one of the reasons why you can become a very prolific researcher, or you can do productive work without kind of getting down to the very deep levels of programming, these GPU chips and things like that. So I think that is something that I think the quantum community has to do. Once you actually build a quantum computer that can do certain things, if you know it does certain things well, we gotta create libraries and packages so that a broader audience can actually use it. So that is actually one important area that I think we'll have to work on. The second question is, can people without advanced degree get into quantum workforce? Absolutely. So at INQ, we have over 350 employees today. Not all of them have quantum physics degrees. Actually, the fraction of people with quantum physics PhD degree is actually relatively small. When you think about system stack, you need people with different kinds of backgrounds. And then they need to come together. And of course, they have to learn quantum. And then the quantum physicists actually have to learn about software and electrical engineering and so on. So it's a highly collaborative work where if you put people together with the right background and skill set and give them the right kind of motivation, we are actually creating the very early stages of key technology, right? So, and here, we don't necessarily require everybody to have a physics and PhD in physics, but I think we need the mindset of people who are willing to jump in and learn. And we absolutely have fresh college graduates that are getting into quantum workforce. And universities like Duke, we actually have master's program to train them. And all of our master's students are being snapped up by quantum computing companies all over the world very quickly. So I think that change is coming. quantum computing is not just for physicists with PhDs, and it shouldn't be. And I think we can actually make better progress faster with a much broader and open mindset today.
Thank you. Any other questions or comments? Okay, if not, let's thank Professor Jungsang Kim. Thank you so much.
Okay, thank you. Hope you have a wonderful meeting. I apologize not being able to come in person. Thank you.
Okay, bye.